Earth is never still. It turns once each day, races around the sun each year, and drifts with the solar system through the Milky Way carried by gravity, guided by ancient light, and sheltered inside a moving magnetic bubble. Tonight, this calm journey follows what Earth is truly moving toward, not a single destination, but a layered path through expanding space, changing interstellar neighborhoods, and shifting cosmic conditions measured with quiet precision. Before settling in, please like the video, subscribe to the channel, and let the steady motion of the universe carry the night gently forward. At the widest scale, the universe is not a still stage. Space itself expands, meaning that the average distance between large, gravitationally unbound galaxies increases with time. This expansion is measured through the redshift of distant galaxies, where light arrives stretched toward longer wavelengths. The farther a galaxy is, the more its light is stretched, and the more its distance increases while the light travels. This pattern is not a simple spray of galaxies flying through pre-existing emptiness. It is a change in the geometry of space, described by models that treat matter and energy as shaping the way distances evolve. In this expanding frame, the phrase moving toward requires careful meaning. Expansion makes most distant galaxies recede on average, not because they are aiming away in a directional sense, but because the scale of space grows. On very large scales, a smooth expansion is often described as the Hubble flow, a statistical pattern where recession speed increases with distance. In this view, there is no central point of expansion inside the universe that everything moves away from. Expansion looks the same from any galaxy on average. Each observer sees distant galaxies receding, and each observer can place themselves at the center of their own map without implying a physical center. Even within an expanding universe, there is still ordinary motion through space. Galaxies have their own velocities relative to the smooth expansion. These departures are called peculiar velocities, meaning motions that are specific to local gravitational environments rather than to the global expansion pattern. Peculiar velocity is not strange in the everyday sense. It is simply the component of motion not accounted for by the average expansion. Gravity creates these local motions. Where matter is denser than average, gravity pulls material inward. Where matter is less dense, material can drift outward relative to the average. Over time, this produces a universe that expands overall while also forming structures such as galaxy groups, clusters, and filaments. Earth participates in both descriptions at once. Earth belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to a small association of galaxies often called the local group. The local group sits within an even larger region of cosmic structure. Each layer has motions driven by gravity and by the initial conditions of the early universe. None of these motions requires a destination that Earth approaches like a target. Instead, Earth moves along trajectories shaped by gravitational wells, while the space between large unbound structures continues to expand. At the largest distances, expansion dominates over the gravitational pull between individual galaxies. A sufficiently distant galaxy's recession due to expansion grows faster than the ability of local gravity to pull it inward. This is why galaxy clusters are the largest bound systems that persist, and why clusters themselves can be separated by expanding space. Within a cluster, gravity holds galaxies together despite expansion. Between clusters, expansion increases separation over time. Earth's long-term motion is therefore a mixture-bound motion within a hierarchy of structures, and participation in a global expansion that sets the backdrop. The expanding universe frame also clarifies a common confusion about speed. A recession speed due to expansion can be greater than the speed of light at very large distances, not because any galaxy locally moves through space faster than light, but because the distance between two far regions of space increases as space expands. Locally, in any small region, the laws of special relativity still apply. No object outruns light in its local neighborhood. The expansion description is a statement about changing distance in a curved spacetime, not about rockets breaking a speed limit. This distinction matters because it shows that the larger scale motion of the cosmos is not experienced as a wind. It is experienced as a pattern in redshifts and distances when the universe is mapped. When Earth is said to be moving, the motion that can be felt directly is small compared with these cosmic descriptions. Earth rotates and orbits. Those motions are measured relative to the Sun and to the stars. Yet the expanding universe frame asks for a different kind of reference. It asks for a calm baseline in which distant galaxies are, on average, at rest with respect to the expansion, and where deviations from that rest are the gravitational flows of structure formation. In this baseline, Earth is not moving toward a single point. Earth is embedded in a flow of matter responding to gravity, while also being carried outward from most distant galaxies by the general expansion. This frame also sets a limit on what the future means in the larger sense. Over billions of years, the universe continues to expand. The details of the expansion depend on the composition of the universe, including ordinary matter, dark matter, and dark energy. The term used for the component that appears to drive an accelerating expansion. Observations indicate that expansion accelerates on the larger scales, meaning that very distant galaxies become increasingly unreachable, in the sense that light sent today may never reach them if they are far enough away. This does not mean nearby bound structures fly apart. It means the cosmic horizon, the region from which light can reach an observer over time, evolves. The expanding universe frame therefore implies that the farthest environment Earth moves through is not a dense medium, but a changing causal landscape defined by expansion. Within this calm geometry, the idea of moving toward becomes meaningful again only when gravity is considered. Gravity creates converging flows. Galaxies in a bound group move toward one another even while the universe expands, because their mutual gravity dominates locally. A familiar example is the Milky Way and the Andromeda Galaxy, which are part of the same bound group and show motion consistent with mutual approach, even though expansion increases distances between unbound systems. This is the pattern that repeats at different scales. Bound structures collapse and merge, unbound structures separate. Earth's motion is therefore towards certain nearby masses within the bound hierarchy, and away from most distant unbound regions in the statistical sense of expansion. At this widest region, the script's focus remains on definition rather than destination. Earth moves through the universe in layered ways, and the largest layer is expansion itself. Expansion is not a force that drags Earth in a direction. It is a property of space that changes the mapping between distant regions over time. The proper question at this outermost level is not where Earth goes in the sense of a point ahead. It is which reference frame is chosen to describe motion. In a purely expanding frame, a comoving coordinate system can be used, where galaxies that follow the Hubble flow remain fixed in coordinates while space expands between them. In such coordinates, large-scale motion becomes a change in scale rather than a movement across a grid. Peculiar velocities then appear as the real motions of galaxies relative to this comoving grid, driven by gravity. This distinction between expansion and peculiar motion sets a quiet foundation. It prevents the subject from becoming a search for a hidden cosmic destination. It grounds the question in measurable physics. Expansion is measured through redshift surveys and the cosmic distance ladder. Peculiar motion is measured through local galaxy velocities and through patterns in the large-scale distribution of matter. Earth's motion can be expressed in either language, but the language changes the meaning of toward. Toward in the expanding frame is not a single arrow. It is a set of gravitational flows superimposed on a stretching space-time. With this wider stage in place, the inward path can now select a practical rest frame used by cosmology to describe large-scale motion more directly. That next region uses the oldest light in the universe as a reference, allowing Earth's motion to be described as a measurable drift through space, rather than as an abstract participation in expansion. A practical way to describe motion on the larger scales is to choose a reference that belongs to the universe itself. The most widely used reference is the cosmic microwave background, a faint glow that fills all directions of the sky. It is the cooled remnant of the early universe when matter and radiation are tightly coupled and the cosmos is hot and dense. As the universe expands, this radiation cools until it becomes microwave light, invisible to human eyes but measurable with sensitive instruments. Because it comes from nearly the same cosmic time in every direction, it provides a natural background against which large-scale motion can be defined. In a perfect idealization, this background would look the same in every direction. Its temperature would be uniform. Its pattern would contain only the tiny fluctuations that represent early density differences. In practice, there is a larger and simpler pattern laid across the background. One side of the sky is slightly warmer, and the opposite side is slightly cooler. This is called the dipole. The simplest and most widely accepted explanation is motion. When an observer moves through a bath of radiation, the radiation appears blue-shifted in the direction of motion and red-shifted in the opposite direction. Blue shift means wavelengths are compressed, which raises the measured temperature slightly. Red shift means wavelengths are stretched, which lowers the measured temperature slightly. The result is a warm direction and a cool direction, a clear compass-like imprint on the sky. This dipole pattern allows a definition of rest. The rest frame is the frame in which the dipole would vanish, leaving only the smaller temperature variations. In that frame, the observer is not drifting through the cosmic microwave background. The background becomes, on average, isotropic, the same in all directions aside from the small primordial fluctuations. This rest frame is not a metaphysical absolute. It is a practical reference tied to a physical signal that permeates the observable universe. It provides a calm baseline for describing how Earth and the solar system move on the larger scales. The concept is important because many other motions can be described relative to it. The solar system moves relative to nearby stars. The Milky Way moves relative to neighboring galaxies. The local group moves within a larger environment. All these motions combine into a net drift that leaves its signature as the microwave dipole. The cosmic microwave background in this use is like a quiet sea of light. Motion through it leaves a subtle wake measured as a temperature gradient across the sky. The rest frame also clarifies how different layers of motion add together. Earth moves around the Sun. The Sun moves through the Milky Way. The Milky Way moves relative to the local group, and the local group has its own motion relative to the larger cosmic environment. Each layer is a vector, a direction and speed, and the net motion is their combined result. The cosmic microwave background does not directly tell the details of each layer. It measures the sum at the observer's location. The layers can then be disentangled using other observations, such as stellar motions, galaxy dynamics, and the Milky Way's rotation. The dipole is the global checkpoint that confirms that these layers combine into a specific measurable drift. The rest frame is also useful because it sits outside the solar system's local complications. Near Earth, the sky is shaped by the Milky Way stars and dust. Nearby stars have their own motions. Even nearby galaxies move within the local group. The cosmic microwave background comes from far beyond all these structures. It is a background that does not belong to the Milky Way. It belongs to the universe's early state. This makes it a stable reference for large-scale motion, a way to define a direction and magnitude of drift that is not dependent on the local distribution of stars. In this frame, the phrase moving toward gains a clean meaning. It becomes a direction in which the solar system is moving relative to the cosmic microwave background. It is not a destination in the sense of an object to be reached soon. It is a heading through space, a direction of drift measured by the temperature dipole. Along that heading, Earth carries its own smaller motions, the daily rotation and the yearly orbit, which add small periodic changes on top of the larger drift. Yet the large-scale direction remains a stable marker of where the solar system is going in a broad sense. The dipole also implies a speed relative to this background. The speed is not measured by timing the arrival of the cosmic microwave background, because it arrives from every direction at the speed of light. The speed is inferred from the size of the temperature difference between the warm and cool directions. A larger difference implies faster motion. This provides a quantitative estimate of the solar system's drift relative to the background. The result is a speed that is large compared with everyday travel and small compared with the speed of light. It is a reminder that cosmic motion can be fast in human terms, while still being slow in relativistic terms. The rest frame is not the same as the frame of cosmic expansion in a strict mathematical sense, but it is closely aligned with it. The cosmic microwave background is emitted when the universe becomes transparent to radiation, and since then the radiation free streams through expanding space. An observer who is co-moving with the average expansion, meaning an observer who follows the Hubble flow without peculiar motion, would see the background with no dipole on average. The dipole therefore measures peculiar motion relative to the Hubble flow. In this sense, the cosmic microwave background provides a practical anchor for the expansion frame. It tells how far the local region, including the Milky Way, deviates from pure comoving rest due to gravity-driven flows. This gravity-driven aspect matters. The dipole is not caused by expansion, it is caused by motion through the background. That motion, in turn, arises from the gravitational history of local structure. The Milky Way and its neighbours form within a cosmic web of matter. Matter flows toward denser regions. Groups and clusters draw in surrounding material. These flows create peculiar velocities. The cosmic microwave background rest frame therefore connects the largest observable light to the local distribution of mass. It turns a temperature pattern into a statement about how matter has pulled the local universe into motion over billions of years. The reference also helps clarify what can change and what remains steady. Earth's rotation speed at the surface depends on latitude. Earth's orbital speed depends on its distance from the Sun along its slightly elliptical orbit. These motions change direction continuously through the day and year. The Sun's motion around the Milky Way is long and slow on human timescales, and the direction changes over millions of years as the Sun traces its galactic orbit. The cosmic microwave background dipole direction is stable on human timescales, changing only very slowly as the solar system's motion changes. This stability is why it can be used as a calm, fixed reference for large-scale drift. The cosmic microwave background rest frame also introduces a subtle perspective on the word truth in the title. Motion depends on reference frames. There is no single universal rest frame demanded by the laws of physics for all contexts. Yet some frames are more useful than others for describing certain problems. For cosmology, the background radiation provides a frame tied to the early universe, making it especially useful for describing large-scale motion. The truth in this sense is not that Earth is moving toward a hidden object. The truth is that Earth's motion can be measured against a universal background, revealing a heading through space that is the sum of many gravitationally shaped motions. This frame also makes it possible to speak calmly about direction without implying fate. The solar system moves through the galaxy and through the local universe. The heading relative to the cosmic microwave background tells where the solar system is going now in a broad kinematic sense. It does not imply that the solar system is on a collision course with the warm spot of the dipole. The warm spot is not a place. It is a direction in the sky defined by light's Doppler shift. The same is true of the cool spot. These are directional markers, not locations. With the cosmic microwave background established as a practical rest frame, the inward path can now move one step closer to measurement. The next region reads the motion imprinted in that background more explicitly, describing how the dipole is extracted from data and how it becomes a clear statement of the solar system's bulk motion through the universe. The cosmic microwave background is measured as a full sky pattern. Instruments map its temperature across millions of directions, producing an image that looks like a softly mottled sphere of tiny variations. Among those tiny variations, one pattern dominates in size and simplicity. One half of the sky slightly warmer, the opposite half slightly cooler. This is the dipole. It is the clearest imprint of large-scale motion available to cosmology, because it arises from a basic physical effect, Doppler shifting of radiation due to an observer's movement. When an observer moves toward a source of light, the observed wavelength is shortened. When an observer moves away, the wavelength is lengthened. For ordinary light sources, this effect changes the color and frequency. For a background radiation field that is nearly uniform, the effect appears as a temperature pattern. The direction of the motion becomes the warm direction, and the opposite direction becomes the cool direction. The size of the temperature difference indicates the speed of motion. This is the same principle that allows astronomers to measure radial velocities of stars by shifts of spectral lines. But here it is applied to a global radiation field that surrounds the observer in all directions. The dipole is extracted by fitting a simple pattern to the sky map. The pattern has a maximum in one direction and a minimum in the opposite direction, with a smooth gradient between. Once this pattern is identified, it can be subtracted to reveal the smaller fluctuations that are of interest for early universe physics. The act of subtracting it is not an arbitrary choice. It is required if one wants to study the primordial variations, because the dipole is so much larger than the rest. Removing it allows the remaining anisotropies to be seen and analyzed. This processing step is a reminder that a large part of modern cosmology is careful separation of signals that have different origins. The interpretation of the dipole as motion is supported by consistency checks. The dipole's shape and frequency dependence match what is expected from a Doppler shift of a blackbody spectrum, the spectrum associated with thermal radiation. The cosmic microwave background is very close to a blackbody, and the dipole shows the correct pattern for a small temperature shift of such a spectrum. This supports the motion explanation. It also supports the idea that the cosmic microwave background is a universal radiation field that is isotropic in a particular frame, and that the observed dipole arises because the observer is not in that frame. From the dipole, a direction in the sky can be assigned. This direction is sometimes described as the direction of motion of the solar system relative to the cosmic microwave background. It is a direction that points toward the warm region of the dipole. In calm terms, this is the heading of the solar system through the large-scale universe, expressed as a direction on the celestial sphere. The direction can be specified in coordinate systems used in astronomy, but the conceptual point is more important. The solar system is moving relative to the background, and the motion has a measurable heading. The dipole also provides a speed estimate. The speed is not large enough to produce dramatic relativistic effects. It is a small fraction of the speed of light, yet it is large in everyday terms, far above speeds associated with planets orbiting or with spacecraft leaving Earth. This speed is the combined result of many layers Earth's orbital motion, the Sun's motion around the Milky Way, and the Milky Way's motion within the local group and beyond. The dipole speed is the net drift at the position of the solar system. The layered nature of this drift is important for what Earth is moving toward. The dipole heading is not controlled by Earth's yearly orbit. Earth's orbit adds a small seasonal modulation to the dipole measurement, because Earth's velocity around the Sun changes direction through the year. This modulation is detectable with precise instruments and is used as a calibration check. The dominant dipole direction remains set by the larger motions of the solar system and the Milky Way. This shows that Earth's motion has a stable large-scale component on human timescales, and that the smaller orbital motion is a periodic ripple on top. The dipole also provides a boundary between local physics and cosmic scale mapping. The largest part of the dipole is local motion, a consequence of gravity in the nearby universe, not a direct consequence of cosmic expansion. This means that the dipole is a map of where gravity has pulled matter. The local universe is not perfectly uniform. Mass concentrations such as galaxy groups and clusters create gravitational acceleration fields that gradually change velocities. Over cosmic time, these accelerations build a drift relative to the background. The dipole is therefore an integrated record of gravitational influences turned into a single velocity vector. The relationship between the dipole and nearby structures is subtle. The dipole tells the net velocity, but it does not identify the specific masses responsible. To connect the motion to mass concentrations, astronomers compare galaxy surveys with velocity fields inferred from redshifts and distance indicators. They map how galaxies cluster and how the local group of galaxies appears to move relative to the larger distribution. These comparisons suggest that the local group's motion is influenced by the gravitational pull of nearby large-scale structures and by the underdensity of nearby voids. The dipole direction therefore points toward a part of the sky where mass concentrations contribute to the local velocity field. Yet the mapping is complex because gravity from many regions contributes, and because the velocity is the sum of past accelerations rather than the result of one present pull. The dipole can also be seen as a reference for the meaning of speed. In the expanding universe, recession speed due to expansion grows with distance. The dipole motion is different. It is a peculiar velocity, a deviation from the smooth expansion. Peculiar velocities are typically hundreds of kilometers per second in the local universe. They are large compared with Earth's orbital speed, but small compared with cosmological recession speeds at great distances. The dipole gives a concrete example of a peculiar velocity in action. It shows that the local universe is not static relative to the background. It is moving in a particular direction, with a particular speed. There are also deeper subtleties that remain uncertain in certain analyses. The cosmic microwave background dipole is generally interpreted as kinematic, meaning purely due to motion. Some researchers explore whether any small part of the dipole could arise from large-scale gravitational effects or early universe asymmetries. But the consensus view remains that the dipole is dominated by motion. The kinematic interpretation fits the data and the expected frequency dependence. Therefore, in a careful documentary, the dipole is treated as a motion signal with high confidence, while acknowledging that fine details of large-scale anisotropy are studied at the level of much smaller fluctuations, not at the dipole level. The dipole also reveals the calm truth about the phrase stranger than we thought. The strangeness does not need sensational claims. It is already strange, in a quiet way. That motion can be read from a temperature gradient across the entire sky. It is strange that the universe provides a background reference older than stars and galaxies. It is strange that Earth's motion through space is not only a local orbit, but a drift measured against ancient light. This is a strangeness grounded in measurement, not in speculation. With the dipole established as the imprint of motion in light, the inward path can now move closer to the gravitational structure that produces the motion. The next region describes the local group of galaxies as a bound moving system, and how the Milky Way and its neighbours drift together through the larger cosmic web. Within the expanding universe, gravity builds islands. These islands are bound systems where mutual attraction overcomes the general tendency of space to stretch distances apart. The local group is one such island. It is a small association of galaxies dominated by the Milky Way and the Andromeda Galaxy, along with the Triangulum Galaxy and dozens of smaller galaxies. In this bound environment, motion is not described primarily by expansion. It is described by orbits, infall, and long gravitational arcs. Earth belongs to the Milky Way, and the Milky Way belongs to this group, so the local group becomes a key layer in what Earth is moving toward. A bound group is defined by a simple principle. The galaxies inside it remain near each other over time because their total gravitational binding is strong enough to keep them from separating with the Hubble flow. Their distances can change, and they can merge, but the system remains a cohesive region of space in which gravity dominates the local dynamics. This is a different regime from the large-scale universe, where galaxies are, on average, carried apart by expansion and only weakly influence one another at large distances. The local group is small compared with galaxy clusters, but it is large compared with the Milky Way alone, and it provides a wider gravitational landscape that shapes the Milky Way's long-term motion. Within the local group, the Milky Way and Andromeda form the central pair. Their combined mass, including large dark matter halos, dominates the group's gravitational potential. Smaller galaxies orbit within this potential, often as satellites of the Milky Way or of Andromeda. Some are irregular galaxies rich in gas. Some are dwarf spheroidal galaxies with little gas and older stars. Their distribution is not perfectly symmetric, reflecting the history of accretion and tidal interaction over billions of years. The group is therefore not a neat sphere. It is a structured collection whose present arrangement is a snapshot of a long assembly process. The local group is also not isolated. It lies near a larger association of galaxies sometimes referred to as the local sheet, and it is part of a broader region that includes the Virgo cluster and other nearby galaxy groups. The local group experiences gravitational pulls from these nearby mass concentrations. These pulls help shape the group's motion relative to the larger universe. In this sense, the local group's drift is both internal and external. Internally, the Milky Way and Andromeda move under their mutual gravity. Externally, the entire group has a bulk motion through space relative to the cosmic microwave background rest frame. This distinction between internal motion and bulk motion is essential. Internal motion describes what happens inside the group. The Milky Way and Andromeda approach each other under gravity, and smaller galaxies orbit within the group's potential. Bulk motion describes how the group as a whole moves relative to a larger reference such as the cosmic microwave background. The bulk motion is what contributes to the dipole signal described earlier. The internal motions contribute less to the dipole because they largely cancel when considering the group's center of mass motion. But they are crucial for describing what Earth is moving toward in the local gravitational sense. In the internal picture, the Milky Way is not moving toward a fixed point. It is moving within a gravitational field dominated by dark matter halos. The Milky Way's halo extends far beyond its visible disk, and Andromeda's halo does the same. The halos may overlap in their outer regions, and their mutual gravity shapes the velocity field between them. This is a quiet kind of motion, unfolding over timescales far longer than a human life. In this setting, Earth is carried along by the Milky Way's motion, and the Milky Way is carried along by the group dynamics. The destination is not a place with a name on a map. The destination is a changing configuration of the group as gravity slowly draws its main members into closer interaction. The local group's bulk motion, meanwhile, reflects a larger gravitational story. The group lies within the cosmic web, the network of filaments and voids formed by the distribution of matter. Gravity causes matter to flow toward denser regions and away from underdense regions in a relative sense. Over time, these flows produce peculiar velocities, the departures from the average expansion pattern. The local group's bulk velocity is part of these flows. It is influenced by the gravitational pull of nearby mass concentrations and by the relative emptiness of nearby voids that do not pull as strongly. The result is a net drift that is measured by the cosmic microwave background dipole and by galaxy velocity surveys. In this layer, the word toward can be used carefully to mean gravitational convergence. Within the local group, Earth is moving toward future configurations where the Milky Way and Andromeda become more strongly interacting, because their mutual gravity draws them closer. This does not require drama in the narration. It is simply a consequence of being inside a bound group with two dominant galaxies. The Milky Way's disk rotates, and its halo extends outward. Andromeda's disk does the same. Over long time, the pair's relative motion leads to eventual close interaction and likely merging. The local group, in this sense, moves toward a future where the dominant members form a single larger system, while smaller satellites are redistributed or absorbed. The group's internal motions also reveal how gravity organizes structure. Smaller galaxies can be tidally stripped, their stars stretched into streams as they orbit within the halos. These streams can persist as faint arcs. They show that the group is still assembling, still drawing in matter and reshaping it. The Milky Way itself contains evidence of past accretion in the form of stellar streams and disrupted satellites. These are local expressions of the same gravitational processes that operate at larger scales. Earth's motion is nested inside this assembly, carried along by the Milky Way's path through the group. The local group's gravity is dominated by dark matter. The visible stars are only traces of a much larger mass distribution. This matters because the group's bulk motion and internal dynamics depend strongly on halo masses and shapes. Halo mass determines how strongly galaxies pull on one another. Halo shape influences orbital paths and the distribution of satellites. These properties are inferred through motions, through the distribution of satellites, and through modeling. Observations indicate the local group is bound and that its dominant members have large halos, but it remains uncertain in detail how halo shapes and masses are distributed and how these details influence the long-term evolution of the group. The group also provides a boundary condition for Earth's cosmic journey. As long as Earth remains bound to the Milky Way, and the Milky Way remains bound within the local group, Earth's large-scale motion is constrained. The group moves through the universe with a bulk velocity, but Earth's local neighborhood remains a bound island. This means that Earth is not drifting freely through intergalactic space. It is carried by a gravitational system that maintains coherence across time. The large-scale drift measured by the cosmic microwave background is the motion of that island, not the motion of a solitary system in an otherwise empty sea. In the local group layer, the truth is both simple and layered. Earth is moving toward a future of closer interaction among the group's dominant galaxies, because gravity binds them and draws them together. Earth is also moving with the local group as the group drifts relative to the cosmic microwave background due to gravity from larger-scale structure. These are not contradictory statements. They describe different scales. One is the internal convergence of a bound system. The other is the bulk drift of that system through a larger cosmic environment. This layer also sets a transition for the inward path. The local group's bulk motion is part of a wider flow field in the nearby universe, influenced by larger mass concentrations beyond the group. To understand that wider influence, the next region moves outward in scale again within the bound hierarchy, describing how the local group relates to the surrounding distribution of galaxies and how gravity organizes their shared drift through space. Beyond the local group, the nearby universe contains larger structures that influence motion through gravity. The local group is bound, but it does not float untouched. It sits within a landscape of galaxy groups, filaments, and clusters. These structures represent mass concentrations, most of it in dark matter, that shape the velocity field of the region. When people ask what Earth is moving toward in a cosmic sense, this is often the layer they mean without naming it. The local group drifts relative to the cosmic microwave background, and that drift reflects gravitational pull from the surrounding distribution of mass, as well as the relative lack of pull from nearby low-density regions. A mass concentration is not only a visible cluster of galaxies. The visible galaxies trace where dark matter is denser. In the cosmic web, matter gathers along filaments and collects in nodes where clusters form. The nearby universe contains several such nodes. They create a gentle acceleration field that acts over millions of years. The local group's motion is the integrated result of this acceleration, accumulated over cosmic time. In a calm view, the local group is not being pulled by a single object like a tether. It is responding to a broad gradient in mass distribution, a sum of many gravitational influences. The idea of moving toward therefore becomes a statement about a direction of net gravitational acceleration. The local group's velocity points along the direction it has been accelerated, and that direction is shaped by where the surrounding matter is denser. Yet density is not uniform in the nearby universe. Some regions contain more galaxies and more dark matter. Other regions are voids, underdense areas with fewer galaxies. A void does not push in the ordinary sense, but because it has less mass, it pulls less. In a field of gravity, being adjacent to a void means there is relatively stronger pull from the opposite side where mass is greater. The local group's motion is influenced by this asymmetry. Large-scale structure is mapped through galaxy surveys. Astronomers measure positions and redshifts of many galaxies and build three-dimensional maps. These maps show filaments and clusters, and also show the empty regions between. Velocity fields are harder. They require distances, not only redshifts, because redshift includes both expansion and peculiar velocity. Distance indicators, such as certain types of stars and supernova, allow the separation of expansion from peculiar motion in nearby galaxies. With these tools, astronomers infer how galaxies deviate from the Hubble flow and thus reconstruct flows toward and away from mass concentrations. These reconstructions indicate that the local group is part of a coherent flow in the nearby universe, shaped by the gravitational landscape. This layer often includes named regions and clusters, but the documentary tone remains cautious about details that can vary with mapping methods. It is sufficient to say that the local group lies near a rich cluster region in the local universe, and that it is part of a broader supercluster scale arrangement of galaxies. The net gravitational influence from nearby clusters and filaments contributes to the local group's drift. This drift is measured by the cosmic microwave background dipole. It is not a hypothesis in the abstract. It is a measured velocity vector that can be compared with the distribution of galaxies to see whether it points toward denser regions. Broadly, the direction is consistent with motion toward regions of higher mass density in the nearby universe. The influence of large-scale structure also clarifies why the title's claim of strangeness can be grounded. It is strange that Earth's motion is shaped by matter that is not visible. The mass that dominates these flows is dark matter, inferred by gravity and by lensing. It is strange that large-scale flows are determined by a network of filaments and voids rather than by a simple uniform field. Yet this strangeness is the expected outcome of structure formation in an expanding universe. Small early fluctuations grow, creating dense nodes and empty voids. Gravity then produces flows toward the nodes. The local group's motion is a local expression of this cosmic process. On the timescales of human life, this motion is almost constant. The acceleration caused by distant mass concentrations is extremely small in the sense of daily experience, but over millions of years it produces hundreds of kilometers per second of peculiar velocity. This is the key to understanding toward in a cosmic context. Toward is not a rapid approach. It is a slow drift that is measurable through its imprint on the cosmic microwave background and through the observed motions of galaxies. Earth's place in this drift is passive. Earth is carried by the solar system and the Milky Way, and those structures are carried by the local group and its surrounding flow field. This layer also introduces the idea that motion can be described relative to different centers. One can describe the local group's motion relative to the cosmic microwave background. One can describe the Milky Way's motion relative to the local group. One can describe Earth's motion relative to the Sun. Each description is valid within its frame. The apparent destination changes with the frame. In the large-scale structure frame, the local group's motion can be described as a drift toward regions where mass density is greater. In the local group frame, the Milky Way's motion can be described as approaching Andromeda. In the solar system frame, Earth's motion is a yearly orbit. The truth is not a single arrow but a nesting of arrows, each with its own context. It is also important to keep the term toward from being interpreted as a future impact event. The local group is drifting through space, but the distances involved are immense. The mass concentrations that influence the drift are far away in intergalactic terms. The drift does not imply that the local group will collide with the specific cluster in any near timescale. Gravity shapes motion, but the universe is expanding and structures evolve. The local group's future is dominated by its internal evolution and by its participation in the local cosmic web, not by an imminent approach to a single external object. Uncertainty remains in the details of the local flow field. The distribution of mass is mapped through galaxies, but the relationship between visible galaxies and total mass involves assumptions about how galaxies trace dark matter. Distance measurements carry uncertainties, and peculiar velocity reconstructions depend on methods. Therefore, while the broad picture of flow toward denser regions is supported, it remains uncertain in detail which specific structures contribute what fraction of the local group's velocity, and how the contributions vary across scales. These uncertainties are part of a living science, not a gap that undermines the basic conclusion. In calm terms, this layer says that Earth is moving with a bound group of galaxies that drifts through the nearby universe along a gravity-shaped flow field. The motion is toward regions where the mass density of the cosmic web is higher, and away in a relative sense from nearby underdense regions that pull less. The heading is measured by the cosmic microwave background dipole and interpreted through maps of the galaxy distribution. The destination is not a single point but a direction of flow in a structured universe. From this large-scale flow, the inward path now returns to a more local but still vast motion, the orbit of the Sun within the Milky Way. This is the motion most directly responsible for the solar system's trajectory through the galaxy, and it is the stage on which Earth's interstellar neighborhood changes over time. Within the Milky Way, the Sun follows a long orbit, and Earth follows with it. This motion is one of the largest, most concrete layers in Earth's journey, because it is a true path through space within a bound system. The Milky Way is a disk galaxy with spiral structure, a central bulge, and a surrounding halo of dark matter. The Sun is embedded in the disk, far from the center compared with the bulge's scale, and it moves around the galaxy under gravity. This orbit is not a perfect circle. It is a broad, slightly wandering path shaped by the Milky Way's mass distribution, by the disk's non-uniform structure, and by the Sun's own velocity relative to the local standard of rest. The Milky Way's disk rotates because the galaxy is a gravitationally bound system with angular momentum. Stars and gas orbit the galactic center, and their orbital speeds depend on the galaxy's mass distribution. Observations indicate that the outer regions rotate faster than would be expected if only visible matter were present, implying a substantial contribution from dark matter in the halo. In this way, the Sun's orbit is guided largely by a gravitational field dominated by dark matter, even though the Sun and nearby stars are the visible traces of the motion. The Sun's orbital period around the Milky Way is long on human scales. It is measured in hundreds of millions of years. During a single human life, the Sun moves only a tiny fraction of a full galactic circuit, yet the motion is real and measurable. The Sun's speed around the galaxy is large compared with Earth's motion around the Sun, even though both are modest compared with the speed of light. The result is a steady drift of the solar system through the Milky Way's disk, carrying Earth through different galactic longitudes and through changing stellar neighborhoods over geological time. Spiral structure adds complexity to this orbit. The Milky Way's disk contains spiral arms, regions where gas and young stars are more concentrated and where star formation is often more active. The exact nature of spiral arms is described in different ways. One common view treats arms as density waves, patterns that move through the disk more slowly than individual stars orbit. In this view, stars and gas pass through arms, spending some time in denser regions before moving on. Another view emphasizes that arms can be transient and can reform and shift with time due to gravitational instabilities, interactions, and the dynamics of gas. These views are not mutually exclusive in all details. Observations indicate that spiral structure exists and that it is not a rigid set of fixed lanes. It is a pattern in the disk that evolves on long timescales. For Earth's journey, the key point is that the Sun's orbit does not lock it permanently inside a single spiral arm. The Sun moves relative to spiral patterns. Over long time, it can pass through more active star-forming regions and then spend long intervals in quieter inter-arm space. These passages matter because star-forming regions contain more massive young stars, and massive stars can produce supernovae on relatively short timescales. The density of stars and the distribution of gas can therefore change the local environment of the solar system, not through immediate dramatic events, but through slow changes in nearby stellar populations and in the interstellar medium the Sun travels through. The Sun's orbit also has a vertical component. The Milky Way's disk has thickness, and stars oscillate above and below the midplane as they orbit. The Sun is not fixed in the plane. It moves in a gentle up and down motion relative to the disk's midplane over long times. This vertical oscillation is a natural result of the gravitational pull toward the disk's mass concentration. The oscillation does not carry the Sun out of the galaxy. It carries it through slightly different densities of gas and dust within the disk's thickness. The midplane tends to be denser in gas and dust than regions above it. Therefore, the Sun's vertical motion can change the average density of interstellar material encountered over time. The Sun's orbit is also not perfectly steady in radius. Small changes in orbital radius can occur over long times due to gravitational interactions with spiral structure and with other mass patterns in the disk. Stars can exchange angular momentum with spiral arms and other features, leading to slow radial migration. The extent of such migration for the Sun remains uncertain in detail. Observations and models indicate that radial migration occurs in disk galaxies, but the exact history for the Sun is not directly measured as a record. It is inferred through models, through the distribution of stellar ages and compositions, and through the present-day orbit. Therefore, while it's plausible that the Sun's orbit has changed somewhat in radius over billions of years, the precise magnitude and direction of that change remain uncertain. The Milky Way also contains non-uniform gravitational features beyond spiral arms. The central region includes a bar-like structure in many disk galaxies, including the Milky Way in modern understanding. The bar can influence the orbits of stars in the inner galaxy, and can drive patterns in the disk. The Sun lies far enough out that bar effects are indirect, but they can still influence the global distribution of mass and the evolution of spiral structure. The galaxy's halo, including dark matter and a population of older stars, provides an additional gravitational field that shapes disk motion and stabilizes the galaxy on large scales. Earth's journey along with the Sun is therefore not a simple loop in empty space. It is a path through a structured gravitational system. The interstellar medium is threaded through this system. Gas and dust between stars are not uniform, and the Sun's orbit determines which regions of this medium the solar system enters. In denser regions, there are molecular clouds, cold and thick enough to form stars. In more diffuse regions, there are warm ionized or neutral clouds. The Sun's motion through the disk means it travels through a changing mix of these environments. These changes can alter the heliosphere, the bubble carved by the solar wind, by changing the external pressure and density of the surrounding interstellar gas. This effect becomes clearer when the narrative later narrows to the local interstellar medium, but the galactic orbit provides the long path that makes such transitions inevitable over time. The Sun's galactic orbit also contributes to the solar system's measured bulk motion relative to the cosmic microwave background. The cosmic dipole measures a net drift, and part of that drift is the Milky Way's motion through the local group and through the nearby cosmic web. Another part is the Sun's orbital motion within the Milky Way. The directions do not align perfectly, and their vector sum produces the net heading. In this way, the Sun's galactic orbit is not only a local story, it is one of the moving parts in the larger motion measured against the oldest light in the universe. Despite this complexity, the Sun's orbit has a calm regularity. It is governed by gravity in a stable galaxy. Over a human lifetime, it changes negligibly in its broad parameters. Over geological time, it traces a long arc that carries Earth through different galactic longitudes, through modest vertical oscillations, and through evolving spiral patterns. The phrase Earth moving toward becomes, at this layer, a movement along the Milky Way's rotating disk. Earth moves toward the next segment of its orbit, toward the next stellar neighborhood, and toward the next interstellar conditions that lie along that path, without implying a single destination point. Uncertainty remains in the fine details of the Sun's historical path. It remains uncertain exactly how spiral arms shift over billions of years and exactly when the Sun passes through denser regions. It remains uncertain how much radial migration occurs in the Sun's history and how that influences the environments encountered. Yet the core facts are stable. The Sun orbits the Milky Way. The orbit is long. The disk is structured and evolving. The solar system therefore travels through a changing galactic environment, not as a dramatic plunge but as a steady drift guided by gravity and shaped by the galaxy's patterns. With the Milky Way orbit set as a major layer of motion, the inward path can now narrow to a more local heading, the Sun's motion, relative to nearby stars in the immediate neighbourhood. This next region describes how the solar system moves through the local stellar field, how that motion is measured, and how it defines a practical direction through the nearest part of the galaxy. In the Milky Way's disk, stars do not move as a perfectly ordered carousel. Each star has its own small difference in speed and direction, relative to the average flow of the local disk. These differences are called peculiar motions in the galactic sense, meaning they are individual deviations from the smooth rotation of the galaxy. The Sun is one of these stars. It follows the broad rotation around the Milky Way, yet it also drifts relative to nearby stars. That drift gives the solar system a practical heading through its immediate neighbourhood, a direction that can be measured and described without invoking distant cosmic structures. Astronomers measure the Sun's local motion by observing many nearby stars and determining their positions and velocities. Position changes across the sky are measured as proper motion, the slow, angular shift of a star's location from year to year. Proper motion is small because the stars are far away, but with precise measurements it becomes clear. Distance is measured through parallax, the apparent shift of a star's position as Earth moves around the Sun. With distance and proper motion, a star's sideways velocity can be calculated. Spectroscopy provides radial velocity, the component toward or away from the observer, measured through Doppler shifts of spectral lines. When these pieces are combined for many stars, the local velocity field is mapped, and the Sun's motion relative to the average of nearby stars can be inferred. This local motion is sometimes described as pointing toward a direction on the sky. The direction is a heading rather than a destination, a way to say which part of the sky the solar system is moving toward relative to nearby stars. The heading is stable on human timescales. It is not fixed on geological timescales because the Sun's galactic orbit and the local velocity field evolve, but within centuries it is effectively constant. This makes it a useful middle layer between Earth's yearly orbit and the galaxy's 100-million-year rotation. It is the direction of travel through the nearest region of the Milky Way, the region where individual stars can be named and measured, and where interstellar gas clouds have local structure. The neighbourhood through which the Sun moves is not empty. It contains stars at a range of distances, as well as interstellar gas and dust. Most stars in the immediate neighbourhood are small and faint compared with the Sun, because small stars are far more common. A few larger and brighter stars stand out, but the dominant population is quiet in visible light at large distances. The neighbourhood also contains star groups that share common motion, remnants of older star-forming regions that have dispersed but still carry similar velocities. The solar system moves among these populations, passing closer to some stars and farther from others over time. The local motion also implies that the pattern of nearby constellations changes slowly. Over thousands of years, the relative positions of stars shift. This is a direct consequence of stars having their own motions through the galaxy. The Sun's motion adds another layer, because the viewpoint itself is moving. Over long time, the solar system changes the region of the Milky Way it samples. Stars that are distant today will be replaced in the night sky by different stars as the sun drifts through the disk. This effect is slow enough that it does not disturb the calm of the present sky. Yet, it is a clear sign that the solar system is not sitting still relative to its local surroundings. In this local frame, the phrase moving toward becomes a statement about what lies ahead in the solar system's path through the interstellar medium. The interstellar medium is the thin mixture of gas, dust, and charged particles between stars. It is not uniform. It contains regions of slightly higher density, regions of lower density, and regions with different temperatures and ionization states. The solar system's motion relative to nearby stars is similar in scale to its motion relative to this gas, because the gas is broadly part of the same rotating disk and is influenced by similar gravitational dynamics. As the sun moves, it encounters different interstellar conditions. These conditions can change the size and shape of the heliosphere, the bubble carved by the solar wind. The changes do not require dramatic events. Even modest differences in interstellar density and pressure can shift the heliosphere's boundary over time. The local heading therefore has physical meaning. It is not only a kinematic arrow on a star map, it points into the region of interstellar space that the solar system will sample next. In that region, there may be warm, partially ionized clouds, cooler, denser regions, or thinner, more rarefied gas. Observations indicate that the Sun is currently embedded in a relatively low-density local environment, compared with dense molecular clouds. This environment is sometimes described as a local cavity or bubble in a broader sense, a region shaped by past supernova activity and stellar winds that have cleared and heated gas. Within that broader cavity, smaller clouds exist, and the Sun moves through them. The precise shapes and boundaries of these clouds remain uncertain because the interstellar medium is difficult to map in 3 dimensions, yet the principle remains. Motion through space means motion through changing interstellar conditions. The Sun's local motion is also accompanied by the Sun's gravitational influence on the nearest region. The solar system's gravity dominates the motion of planets and smaller bodies, and it extends outward into a region where it competes with the gravitational influence of passing stars and the galaxy's tidal field. The boundary of the solar system in this sense is sometimes described through the distribution of distant icy bodies and the stability of their orbits over time. Passing stars can perturb these distant bodies, and such perturbations depend on the relative motion of stars. The Sun's motion through the local stellar field therefore has consequences for the most distant parts of the solar system, not in immediate visible weather, but in slow gravitational shaping over long time. The local motion also influences the long-term exposure of Earth to certain kinds of energetic particles. The heliosphere modulates cosmic rays, and the heliosphere's size depends partly on the interstellar medium. If the solar system moves into a denser region, the external pressure increases and the heliosphere can contract. A smaller heliosphere can allow more galactic cosmic rays to reach the inner solar system, depending on the Sun's magnetic activity and on the details of particle transport. If the solar system moves into a less dense region, the heliosphere can expand, potentially reducing cosmic ray penetration. Observations indicate that the heliosphere responds to external conditions, but it remains uncertain how large the effect on Earth's surface environment is for typical interstellar variations, because Earth's atmosphere and magnetic field provide strong additional shielding. The key point is that the local heading defines a path through a medium that can alter the solar wind bubble over time. The measurement of a local motion also clarifies a limit. Even though the solar system moves quickly in everyday units, the distances between stars are immense. the Sun's drift changes the stellar neighborhood on long timescales, not on human timescales. Close stellar encounters that significantly disturb the inner solar system are rare. Most stars pass at distances that are large compared with planetary orbits. The local motion therefore produces a steady change in background rather than a constant series of near passes. The sky evolves slowly. The interstellar medium changes slowly. The heliosphere boundary shifts over long time. The effect is gentle in the present, even though the underlying motion is continuous. In this region, the meaning of stranger than we thought remains grounded. It is strange, in a quiet way, that Earth is carried through the galaxy not only by a large orbit around the galactic center, but also by a drift through the local stellar field, measurable through the motions of nearby stars. It is strange that the interstellar medium is a real environment with structure, and that the solar system moves through it like a ship through changing water, even though the medium is so thin that it feels like nothing. These are not dramatic revelations. They are measured aspects of how a star like the Sun lives inside a galaxy. With the Sun's local motion established as a heading through nearby stars, the inward path now moves into what lies between those stars. The next region focuses on the interstellar medium ahead of the solar system, describing its composition, its phases, and how small changes in density and ionization can matter for the heliosphere that surrounds Earth. Between the stars, there's a medium so thin it would be called a vacuum by most terrestrial standards, yet it fills the galaxy and carries a measurable structure. This interstellar medium is a mixture of gas, dust, magnetic fields, and energetic particles. It is not uniform. It forms clouds of different densities and temperatures, and it also forms low-density cavities where gas is warmer and more ionized. The solar system moves through this medium as it orbits the Milky Way and drifts relative to nearby stars. Along that motion, the external conditions around the Sun change, and those changes subtly reshape the boundary of the Sun's influence. The interstellar gas is mostly hydrogen, with helium as the next most abundant element and smaller amounts of heavier elements. Hydrogen appears in different forms. It can be neutral, with its electron bound to the proton. It can be ionized, with the electron removed, forming plasma. It can also be molecular, where hydrogen atoms bind into molecules in cold, dense regions. These forms correspond to different physical environments. Neutral hydrogen is common in warmer diffuse clouds. Ionized hydrogen is common in regions influenced by hot stars, supernova remnants, and the general background of ultraviolet radiation. Molecular hydrogen forms in the cold, dense interiors of clouds where dust grains shield the gas from ultraviolet radiation and allow molecules to survive. Dust is a small mass fraction but a large influence. Dust grains are tiny solids made of silicates, carbon-rich compounds, and ices in colder regions. They scatter and absorb starlight and irradiate energy in infrared. They also provide surfaces on which molecules can form. Dust is therefore part of the chemistry of the interstellar medium as well as part of its appearance. The distribution of dust traces the distribution of gas, but it does not match perfectly because dust can be processed and destroyed in shocks and can also be concentrated by turbulence. The interstellar medium contains phases, a practical way of grouping environments by typical density and temperature. There is a cold neutral phase with higher density and lower temperature. There is a warm neutral phase with lower density and higher temperature. There is a warm ionized phase where gas is partly ionized. There is a hot ionized phase in very low density regions that can be heated by supernova explosions. These phases mix and coexist, and boundaries between them can be complex. The solar system can pass from one phase to another over time, not as a sudden wall, but as a gradual transition through regions with changing density and ionization. The local region around the Sun is often described as relatively low density compared with dense molecular clouds. Observations indicate that the Sun is embedded in a local interstellar environment shaped by past energetic events, including supernova activity that can carve cavities and heat gas. Within this broader low-density region, smaller clouds of warmer gas exist. The Sun moves through them. The boundaries of these clouds are not mapped like coastlines because interstellar gas is hard to place in 3 dimensions. Its structure is inferred through absorption lines in the spectra of nearby stars, through emission from neutral hydrogen, and through measurements of interstellar dust. These methods provide a partial map that supports the view of a clumpy local medium, with the solar system traveling through patches of differing density. As the solar system moves, the interstellar medium ahead becomes the external pressure that the solar wind must push against. The solar wind is a continuous flow of charged particles, mainly protons and electrons, streaming outward from the Sun. It carries the Sun's magnetic field into space, forming a rotating magnetic structure. Where the solar wind expands outward, it eventually encounters the interstellar medium and is slowed and deflected. The region dominated by the solar wind and its magnetic field is called the heliosphere. It is not a rigid sphere. It is a bubble shaped by the solar wind's strength and by the interstellar medium's density, pressure, and magnetic field. When the interstellar density increases, the external pressure increases. A stronger external pressure can compress the heliosphere, moving its outer boundary inward. When the interstellar density decreases, the heliosphere can expand. Ionization matters as well because the interstellar medium can exchange particles with the heliosphere through charge exchange, a process where an ion captures an electron from a neutral atom, changing both particles' states. This exchange influences the structure of the boundary region and can create populations of energetic neutral atoms that travel long distances. It also influences the distribution of neutral atoms that penetrate into the inner heliosphere, where they can become ionized and picked up by the solar wind. The interstellar magnetic field also shapes the heliosphere's boundary. Magnetic pressure and magnetic tension can distort the heliosphere, making it asymmetric. The direction of the interstellar field relative to the Sun's motion and the solar magnetic field affects how the boundary region forms. A stronger interstellar field can provide additional pressure that confines the heliosphere. A different field orientation can change the shape of the outer boundary and the direction of flows around it. The solar system's motion through the local medium therefore has a magnetic aspect as well as a density aspect. The phrase Earth moving toward becomes, at this layer, a movement toward different boundary conditions. It is a movement toward patches of interstellar gas with slightly different density, temperature, and ionization. It is a movement toward different magnetic field orientations and strengths. These differences change how far the heliosphere extends and how it deflects energetic particles. They also change the population of neutral atoms that drift into the solar system and the distribution of dust grains that pass through. The changes are typically gradual and subtle, yet they matter because the heliosphere is a dynamic shield that modulates the environment of the inner planets. Cosmic rays provide one of the clearest connections between interstellar conditions and Earth. Galactic cosmic rays are high-energy particles arriving from outside the solar system. Their sources include supernova remnants and other energetic processes in the galaxy. The heliosphere's magnetic field and solar wind slow and deflect many of these particles, especially at lower energies. The efficiency of this modulation depends on solar activity and on the heliosphere's size and structure. If the heliosphere contracts due to higher external pressure, modulation can change, potentially allowing a higher flux of some cosmic rays into the inner solar system. If it expands, modulation can strengthen. The effect at Earth's surface is further buffered by Earth's magnetic field and atmosphere, which provide strong shielding. Therefore, changes in the heliosphere do not translate directly into dramatic changes at ground level. Yet the pathway exists, and it is a real part of the environment through which Earth moves. The interstellar medium also carries dust grains that can enter the heliosphere. Some interstellar dust is deflected by magnetic fields, while some penetrates. The distribution of interstellar dust within the heliosphere depends on grain size, charge, and the magnetic environment. These grains can be detected by spacecraft instruments. Their presence shows that the boundary between the solar system and the interstellar medium is permeable to some material. It is a filtered boundary rather than a solid barrier. As the solar system moves into regions with different dust densities or different ionization conditions, the dust flow into the heliosphere can change. These changes are part of the broader story of Earth moving through environments, not toward a single end point. The local interstellar medium is also shaped by time and by the lives of nearby stars. Massive stars emit strong ultraviolet radiation and drive winds that ionize and shape surrounding gas. When such stars end as supernovae, they inject energy that heats and stirs the medium, creating hot bubbles and shock fronts. Over long time, the medium becomes a patchwork of warm clouds and hot low-density cavities. The sun's motion carries it through this patchwork. The next region of travel is not chosen by intention. It is determined by the sun's velocity vector and by the structure of the medium that happens to lie along that path. Uncertainty remains because mapping the interstellar medium is difficult. Distances to clouds are inferred with limited sampling, because absorption measurements require background stars and because the medium is complex and turbulent. It remains uncertain exactly how cloud boundaries are shaped in 3 dimensions, and exactly how quickly the sun moves from one local cloud to another. It also remains uncertain how interstellar magnetic field variations along the path will reshape the heliosphere on longer timescales. Observations indicate that the local medium is structured and that the heliosphere responds to external conditions, but the precise future sequence of environments along the sun's path is not fully known. This layer completes a calm idea. Earth moves through a real interstellar environment, thin yet structured, and that environment sets the external conditions that shape the heliosphere. Earth is not moving toward a single cosmic object here. Earth is moving toward varying densities, temperatures, ionization states, and magnetic fields in the gas between stars. The change is slow, but it is part of the truth of Earth's journey. The inward path now moves from the interstellar medium itself to the heliosphere as a moving shield. The next region focuses on how the solar wind carves a boundary, how that boundary shifts with external conditions, and how this shifting bubble defines the immediate space environment of the planets as Earth continues along its layered motion. The heliosphere is the sun's moving boundary in space. It is created by the solar wind, a continuous stream of charged particles flowing outward from the sun, carrying the solar magnetic field with it. This flow expands until it meets the interstellar medium, where external pressure and magnetic fields push back. The result is a broad bubble surrounding the solar system, not perfectly spherical, shaped by the direction of the sun's motion and by the interstellar environment. Earth lives deep inside this bubble. As the solar system moves through the galaxy and through different interstellar conditions, the heliosphere shifts and changes shape. In this way, Earth moves not only through space, but through a changing shield. The solar wind begins in the Sun's corona, the hot outer atmosphere where temperatures are high enough that gas exists as plasma. In this plasma, particles have enough energy to escape the Sun's gravity and stream outward. The solar wind is not uniform. It has faster and slower components, and it varies with solar activity. The Sun's magnetic field shapes the wind's flow and carries structure outward in a spiral pattern because the Sun rotates. The result is a magnetic field embedded in the wind that extends throughout the inner solar system and beyond. As the solar wind expands, it cools and becomes less dense. Far from the Sun, it remains supersonic relative to the local sound speed in the plasma, meaning it moves faster than pressure waves can travel through it. Eventually, the outward wind is slowed by the pressure of the surrounding interstellar medium. The region where the solar wind transitions from supersonic to subsonic flow is often described as a termination shock. Beyond that region, the wind is slower and more turbulent. Farther still, the solar wind and interstellar medium meet at a boundary region, where the pressure balance is achieved. This boundary is not a thin shell. It is a complex region with mixing, charge exchange, and magnetic field interactions. The outermost boundary, where the solar wind's influence gives way to the interstellar medium, is often described as the heliopause. The heliosphere's size and shape depend on two main factors: the strength of the solar wind and the conditions of the interstellar medium. If the solar wind is stronger, it pushes outward more effectively, expanding the bubble. If the interstellar medium is denser or has stronger magnetic pressure, it compresses the bubble. Because the solar wind varies with the solar cycle, the heliosphere breathes. It expands and contracts modestly over time. Because the solar system moves through a structured interstellar medium, the boundary conditions also change on longer timescales, shifting the overall size and asymmetry of the heliosphere. The Sun's motion through the interstellar medium creates an upstream and downstream direction for the heliosphere. Upstream is the direction from which the interstellar medium effectively flows into the heliosphere due to the Sun's motion. Downstream is the opposite, where the heliosphere trails. This produces a shape that can be described as a blunt nose and an extended tail, though the tail's details are complex and can be influenced strongly by magnetic fields and charge exchange processes. The nose region is where external pressure is highest, and it is where changes in interstellar density and magnetic field most directly compress or reshape the heliosphere. The solar system moves toward that nose direction as it travels through space. Earth, embedded far inside, is carried along, and the heliosphere's leading boundary responds to what lies ahead. Charge exchange plays a central role in the boundary region. Neutral atoms from the interstellar medium can penetrate the heliosphere because they are not deflected by magnetic fields. When a neutral atom interacts with a solar wind ion, an electron can transfer, turning the ion into a neutral atom and the neutral into an ion. The newly created energetic neutral atom can travel long distances in straight lines, carrying information about the region where it formed. Instruments can detect these energetic neutral atoms and create global maps of the heliosphere's boundary conditions. This method provides a way to observe the heliosphere's shape and pressure distribution without sending spacecraft to every direction. Neutral atoms that penetrate deeper can become ionized by sunlight or by collisions, and then be picked up by the solar wind. This pickup process adds mass and changes the wind's momentum. It is another way the interstellar medium influences the solar wind flow inside the heliosphere. The effect depends on the density of neutral atoms outside and on the solar wind conditions. Therefore, as the solar system moves into regions with different neutral density, the internal behavior of the heliosphere can shift. For Earth, the heliosphere acts as a filter for galactic cosmic rays. Galactic cosmic rays are high-energy particles arriving from outside the solar system. The heliosphere's magnetic field and turbulent plasma reduce the flux of many of these particles, especially at lower energies. This modulation depends strongly on solar activity. During higher solar activity, the solar wind and magnetic field tend to be stronger and more disturbed, leading to reduced cosmic ray intensity at Earth for many energies. During lower solar activity, cosmic ray intensity increases. This is a well-observed cycle. The heliosphere's size and shape, influenced by interstellar conditions, also affect modulation, though the solar cycle often dominates on short timescales. Earth's own magnetic field and atmosphere provide additional shielding, so changes in heliospheric modulation do not translate directly into dramatic changes at the surface. Yet cosmic rays matter for the upper atmosphere, for satellite electronics, and for radiation exposure in spaceflight. Cosmic rays also create secondary particle showers in the atmosphere and contribute to ionization rates. Therefore, a changing heliosphere changes a part of Earth's space environment even when the ground level remains stable in daily experience. The heliosphere also interacts with dust. Interstellar dust grains can enter the heliosphere, but their trajectories are influenced by electromagnetic forces because many grains carry charge. The solar wind's magnetic field can deflect smaller charged grains more strongly than larger ones. Therefore, the heliosphere filters dust by size. As the solar system moves into regions with different dust density or magnetic orientation, the dust flow into the inner solar system can change. This is part of the subtle material exchange across the boundary. The long-term motion through the galaxy implies that the heliosphere has not always been as it is now, and will not remain exactly as it is. In denser interstellar regions, a smaller heliosphere is expected. In very low-density regions, a larger heliosphere is expected. The Sun's present local environment appears to be relatively low density, and the heliosphere is correspondingly large. Over time, as the solar system moves, the boundary could shift. The consequences for Earth depend on the magnitude of the change and on Earth's own shielding. Most interstellar variations expected in the local neighborhood likely produce modest changes rather than extreme ones, but it remains uncertain how large the variation can be along the Sun's path, because the interstellar medium structure is complex. This heliosphere layer gives a calm meaning to toward. Earth moves toward whatever interstellar conditions lie ahead of the Sun's motion, and those conditions shape the size and properties of the heliosphere. Earth remains inside the bubble, but the bubble's boundary is a moving frontier that responds to the medium. The truth is that Earth is sheltered by a dynamic system, not by an unchanging wall. The strangeness is that the solar system carries its own space weather boundary through the galaxy, and that boundary changes quietly as it travels. With the heliosphere established as the moving shield, the inward path now narrows to solar activity itself. The solar wind and the magnetic field change over the solar cycle and in longer trends. Those changes modulate the heliosphere and affect Earth's space environment on timescales of years and decades. The next region therefore focuses on the Sun's activity cycles as the immediate driver of the most noticeable variations in the shield Earth lives within. The Sun is not constant in its activity. Its magnetic field changes, and those changes shape the solar wind and the space environment of the planets. The most familiar pattern is the solar cycle, a repeating variation in sunspots, magnetic complexity, and eruptive events. This cycle modulates the heliosphere from the inside, affecting how strongly it deflects cosmic rays and how often storms of charged particles travel outward. In the larger journey described earlier, the heliosphere responds to the interstellar medium on long timescales. but on the timescale of human experience, the dominant variation comes from the Sun itself. Earth moves through space under this shifting magnetic weather, carried along by the larger motions while experiencing the nearer rhythm of the solar cycle. Sunspots are visible markers of magnetic regions on the Sun's surface. They appear dark because they are cooler than surrounding areas, caused by strong magnetic fields that inhibit convection. When sunspots are numerous, the Sun's magnetic field is more complex. During such times, the Sun tends to produce more frequent flares and coronal mass ejections. A flare is a rapid release of energy in the Sun's atmosphere, producing intense radiation across many wavelengths. A coronal mass ejection is an ejection of plasma and magnetic field into space. These events can travel through the solar wind and interact with Earth's magnetic field, producing geomagnetic storms and auroras. The solar cycle is often described by the rise and fall of sunspot counts over about 11 years, with the Sun's magnetic polarity reversing over a longer cycle of about 22 years. The precise length varies from cycle to cycle. The cycle arises from a dynamo process inside the Sun, where the motion of conducting plasma generates and reorganizes magnetic fields. The dynamo involves differential rotation, where the Sun rotates at different speeds at different latitudes, and convection, where plasma rises and sinks. These motions twist and stretch magnetic field lines, building and reorganizing the Sun's magnetic structure over time. The details of the dynamo are complex, but the existence of the cycle is strongly supported by centuries of observation. The solar wind responds to the cycle. During times of higher activity, the solar wind can become more disturbed, with more shocks and magnetic irregularities. These irregularities scatter cosmic rays more effectively, reducing the cosmic ray intensity reaching the inner solar system for many energies. During quieter times, the solar wind is less disturbed and cosmic ray intensity increases. This cycle in cosmic rays is measured by detectors and is a clear example of how the Sun's magnetic behavior modulates Earth's space environment. Earth's magnetosphere, the region dominated by Earth's magnetic field, responds to solar wind conditions. When a coronal mass ejection arrives, it can compress the magnetosphere and inject energy into it, driving currents and disturbances. These disturbances can produce auroras and can affect satellites and power systems. The strength of these effects depends on the properties of the arriving plasma and magnetic field, and on the orientation of the interplanetary magnetic field relative to Earth's field. A strong southward magnetic component can couple more efficiently to Earth's field, allowing more energy transfer into the magnetosphere. These interactions are part of space weather, a term used for the varying conditions in space driven by the Sun. In the context of what Earth is moving toward, the solar cycle provides an important clarification. Earth is not moving toward a single distant event. It is moving through repeated phases of solar magnetic change. Each year, Earth experiences a slightly different solar wind environment. Over a decade, it experiences a full cycle of rising and falling activity. This is a near-term rhythm compared with the Sun's galactic orbit and the local group's drift. Yet it is the rhythm that most strongly shapes the conditions experienced by satellites, astronauts, and the upper atmosphere. The solar cycle also changes the heliosphere's structure. The heliosphere is filled with the solar wind and embedded magnetic fields. When the Sun is more active, the heliospheric magnetic field can become stronger and more irregular. This affects the transport of energetic particles, including cosmic rays and solar energetic particles produced by flares and shock fronts. Solar energetic particles can arrive at Earth within minutes to hours after an event. Depending on particle energy and magnetic connectivity, These particles can increase radiation levels in space and in the upper atmosphere. Their occurrence is more likely during active periods, though strong events can occur at any time. Earth's atmosphere provides significant protection against energetic particles. Even so, the upper atmosphere is sensitive to changes in solar ultraviolet radiation, which also varies over the solar cycle. Increased ultraviolet can heat the upper atmosphere, causing it to expand. This increases atmospheric drag on satellites in low Earth orbit, changing their trajectories and requiring more frequent orbit adjustments. The changes are measurable and are part of how the Sun's cycle affects human technology. The effects are not constant, they rise and fall with the cycle's phases. There are longer-term variations as well. The Sun can undergo multi-decade periods of lower or higher activity compared with typical cycles. The historical record includes periods of low sunspot counts, though interpreting past variability requires careful calibration. Such long-term variations can influence cosmic ray modulation and can influence the energy input to the upper atmosphere. Yet the Sun remains a stable main sequence star on long timescales, and these variations remain within a bounded range compared with the changes expected over billions of years as the Sun slowly evolves. The near-term truth is that solar magnetic cycles continue and remain the dominant driver of variability in Earth's space environment. The solar cycle also ties back to the heliosphere's interaction with the interstellar medium. The external medium sets the overall boundary conditions, but the Sun's activity sets the internal pressure and magnetic field that push against those conditions. A more active Sun produces a stronger wind and magnetic field, potentially expanding the heliosphere modestly. A less active Sun reduces pressure, allowing the heliosphere to contract. Therefore, the heliosphere's size and shape vary due to both internal and external drivers. On decade timescales, internal solar variability dominates. On longer timescales, the interstellar environment can shape the mean state around which solar cycles oscillate. In calm terms, this layer makes the title less mysterious and more precise. Earth moves through space as the Sun's magnetic system cycles. The truth is not that Earth approaches an unknown cosmic boundary. The truth is that Earth is embedded in changing magnetic weather, with predictable cycles and occasional bursts. The strangeness lies in scale. A magnetic cycle driven inside the Sun produces effects that can be measured far beyond Earth, and the whole heliosphere responds. The solar system carries this changing shield through the galaxy, while Earth continues its daily and yearly motions within it. Uncertainty remains in detailed prediction. The timing and strength of individual solar storms are difficult to forecast far in advance. The exact peak strength of a solar cycle can vary, and the detailed magnetic configuration that produces strong events is complex. These uncertainties are acknowledged because they reflect the chaotic elements of magnetized plasma systems. Yet the existence of the cycle and its broad effects are well established. With the solar cycle established as the dominant near-term driver of heliospheric variability, the inward path now narrows further to Earth's own motion around the Sun. This next layer grounds motion in a speed and direction that can be described simply and measured directly, adding a periodic vector to the larger drift through space. Earth's motion around the Sun is the nearest large-scale motion in the layered journey. It is steady, repetitive, and measured with great precision. Each year, Earth traces an orbit that is close to a circle but slightly elliptical. This orbit determines the cycle of seasons through the tilt of Earth's axis. It also contributes a significant part of Earth's speed through space, adding to the Sun's larger motion through the Milky Way and the local group. In this layer, moving toward becomes a simple geometric fact. Earth is always moving toward the next point on its orbit, and the direction of that motion changes continuously as the orbit curves. Earth's orbit is governed by gravity. The Sun's mass dominates the solar system, and Earth's motion is a balance between inertia and the Sun's gravitational pull. Without gravity, Earth would move in a straight line. With gravity, the line bends into a closed path. The orbital speed is not constant because Earth's distance from the Sun changes slightly along the ellipse. Earth moves a little faster when closer to the Sun and a little slower when farther away. This variation is modest but real, and it is part of how orbital mechanics works in a central gravitational field. The shape of the orbit is described by orbital elements. One element is the semi-major axis, which sets the orbit's overall size. Another is eccentricity, which measures how stretched the ellipse is. Earth's eccentricity is small, meaning the orbit is close to circular. The small eccentricity helps keep Earth's solar energy input relatively stable across the year, compared with what would occur on a more eccentric orbit. The remaining seasonal changes in sunlight are dominated not by distance, but by axial tilt, which changes the angle at which sunlight strikes different latitudes and the length of day. Orbital speed can be expressed in kilometers per second, and it is large in everyday terms, over an hour. Earth travels a distance comparable to several times around the planet. Over a day, Earth travels far along its orbit. Yet this motion is not felt directly because it is free fall, a state where Earth and everything on it accelerate together under gravity. The experience on the surface is of weight supported by local forces, while the orbital motion is part of the planet's overall trajectory through space. The orbital velocity is also a vector, a direction and magnitude. Over the course of a year, the direction of Earth's orbital velocity changes as Earth moves around the Sun. This means that Earth's total velocity through space, when combined with the Sun's galactic and local motions, varies slightly in direction over the year. This variation is important for precision measurements, including the measurement of the cosmic microwave background dipole and the detection of tiny signals in astrophysical data. The annual change provides a known modulation, and that modulation can be used to check instrument calibration. In this way, Earth's orbit becomes part of the measurement system of modern astronomy. Earth's orbital motion also changes the perspective on the sky through parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. This shift is small and requires precise measurement, but it is the basis for the fundamental method of measuring distances to nearby stars. Parallax turns Earth's orbit into a baseline for cosmic measurement. This is another quiet strangeness. The same motion that carries Earth through space is used to measure the scale of the universe, because it provides a known geometry. Earth's orbit also determines the distribution of sunlight and energy that drives climate. While this script avoids sensational claims, it is part of scientific reality that small changes in orbital parameters over long time can alter climate patterns. These changes are driven by gravitational interactions with other planets, especially Jupiter and Saturn. The orbital parameters vary on timescales of tens of thousands to hundreds of thousands of years. The changes affect eccentricity, axial tilt, and the orientation of the orbit in space. These variations can change the seasonal and latitudinal distribution of sunlight. They are part of the long-term climate system and are studied in geology and paleoclimate. In the present, the orbital changes are slow, but they exist and are part of what Earth moves toward over geological time. The orbit also defines Earth's motion through the solar wind environment. The solar wind flows outward from the Sun, and Earth's orbit carries it through a changing heliospheric longitude. The solar wind itself is not uniform, and it varies with solar rotation, and with the solar cycle. Earth, therefore, experiences variations in solar wind speed and magnetic field, not only because the Sun changes with time, but because Earth's position in the heliosphere changes through the year. These variations are smaller than the solar cycle effects and are often dominated by the structure of the Sun's rotating wind, yet they contribute to the detailed pattern of space weather conditions experienced near Earth. In the phrase "moving toward," Earth's orbit provides a grounded meaning that requires no cosmic mystery. Earth moves toward its next orbital position, and, in doing so, moves toward changing seasons and changing sky perspectives. Earth's orbit also adds to Earth's overall speed through space, a speed that combines with the Sun's motion through the Milky Way and the local group. This combined speed is a simple vector sum, though the full vector is not experienced directly. It is inferred from measurements and from known orbital mechanics. Uncertainty in this layer is small compared with other layers. Earth's orbit is measured precisely. Its parameters are known. The small long-term variations are also well described by celestial mechanics, though their detailed future depends on the chaotic aspects of multi-body gravitational systems over very long times. For the purposes of a calm documentary, the key point is stability. Earth's orbit is regular. It provides a steady rhythm on which all other motions are layered. This stable orbital layer prepares the inward path for an even more immediate motion, Earth's daily rotation. Rotation determines how fast points on Earth's surface move through space each day, and it depends on latitude. It is the motion most closely tied to the experience of day and night. Yet it is also a significant speed in physical terms. The next region narrows from the year to the day, describing Earth's rotation and how it adds another component to Earth's total motion through space. Earth rotates, and this rotation is the motion most closely tied to everyday time, day and night, sunrise and sunset, and the apparent sweep of the sky are all expressions of a planet turning in space. Rotation also contributes a real speed to every location on Earth's surface. That speed depends on latitude, near the equator. The surface moves fastest because it traces the largest circle around Earth's axis. Near the poles, the surface moves slowly because it traces a much smaller circle. In the layered journey of Earth through the universe, rotation is the most local layer, yet it is still a substantial physical motion. Rotation can be described in two closely related ways. One is the length of a day as experienced from the ground, the time between one noon and the next. This is the solar day, defined by the Sun returning to the same position in the sky. The other is the time it takes Earth to rotate once relative to distant stars, the sidereal day. The sidereal day is slightly shorter because Earth is also moving around the Sun while it rotates. Each day, Earth must rotate a little more than one full turn relative to the stars to bring the Sun back to the same place in the sky. This difference is small in daily life, yet it is fundamental in astronomy and navigation, and it shows how layered motions interlock even in the simple act of defining a day. Earth's rotation speed at the surface is determined by the planet's circumference at a given latitude and the rotation period. At the equator, the circumference is the largest, and the surface speed is the greatest. As latitude increases, the effective circumference decreases because the circle traced by a point on the surface shrinks by the cosine of latitude. In practical terms, a person standing on the equator is carried around Earth's axis at a speed that is far greater than a person standing at high latitude. Even though both complete a full rotation in the same time, this is not a difference in how fast the planet turns. It is a difference in the size of the circular path traced by the surface. This rotation speed is not felt as wind because it is shared by the ground, the air, and the oceans in a broad sense. The sensation of motion comes from changes in speed, not from steady motion. Earth's rotation is steady enough that it is experienced as stillness. Yet rotation has measurable effects. One of the most important is the Coriolis effect, the tendency for moving air and water to curve in a rotating frame. The Coriolis effect shapes global wind patterns and ocean currents, and it helps organize storms. It does not create motion by itself. It alters the direction of motion that already exists. Its strength increases with latitude and is zero at the equator, which means the influence of rotation on horizontal motion differs from place to place. Rotation also contributes to Earth's shape. A rotating fluid body tends to bulge at the equator due to centrifugal effects, a tendency for moving mass to resist being pulled into a tighter circle. Earth is not a perfect sphere. It is slightly flattened at the poles and bulged at the equator. This shape is maintained by the balance between gravity pulling inward and rotational effects pushing outward. The bulge is small compared with Earth's radius, yet it is measurable and important in geodesy, the science of measuring Earth's shape and gravitational field. The bulge also affects the local value of gravity and the distribution of mass, which in turn affects precise satellite orbits and the long-term behavior of Earth's rotation. Rotation influences timekeeping as well. Modern time is defined using atomic clocks, which measure time by the frequency of atomic transitions. Earth's rotation is not perfectly constant, and it varies slightly due to the exchange of angular momentum between the solid Earth, the oceans, and the atmosphere, as well as due to tidal interactions with the Moon. Because of this variability, the relationship between atomic time and mean solar time slowly drifts. Adjustments are occasionally required to keep civil time aligned with Earth's rotation. This is a subtle sign that even the daily turning of the planet is part of a larger dynamical system, influenced by fluid motion and gravitational coupling. Earth's rotation also has a direct astronomical consequence. It sets the apparent motion of the sky. Stars appear to rise in the east and set in the west because Earth rotates eastward. The celestial sphere appears to spin around a point near the celestial pole in each hemisphere. This apparent motion is used in navigation and in telescope tracking. A telescope must track the sky's rotation to remain fixed on a star. The predictability of this rotation makes it a stable base for observing the universe. Yet the axis of rotation itself is not fixed in an absolute sense. It undergoes slow changes in orientation, which will be addressed in a later layer. For the moment, rotation is treated as a steady daily turning with a measurable period. At the surface, the rotation speed also interacts with altitude. A point at higher altitude is slightly farther from Earth's axis at a given latitude, so it moves slightly faster than a point at sea level at the same latitude. The difference is small compared with the overall speed, but it is real in precise measurements. Such differences can matter. They contribute to tiny changes in clock rates through relativity, because motion and gravity both influence timekeeping at high precision. In everyday life, these effects are invisible, yet they show again that Earth's rotation is a physical motion with measurable consequences even when it feels like rest. The daily rotation also interacts with Earth's orbit in a way that shapes the rhythm of sunlight. A solar day is defined by the sun's position, and the sun's apparent motion across the sky is a combined effect of Earth's rotation and Earth's orbit. Over the year, the length of apparent solar time varies slightly due to the tilt of Earth's axis and the elliptical shape of Earth's orbit. This produces a difference between mean solar time and apparent solar time, described by a correction sometimes called the equation of time. The correction is a reminder that even the daily cycle contains the imprint of Earth's yearly motion. The planet's timekeeping is not a single motion but a weave of motions. In the context of what Earth is moving toward, rotation provides a grounded meaning that does not depend on distant cosmic objects. Earth moves toward the next sunrise at every location because the planet turns. It moves toward the next local noon and the next local night. It moves toward a changing relationship between each place and the sun's direction through the day. At the same time, rotation adds another velocity component to Earth's total motion through space. That component is directed eastward at the surface, tangent to the circle traced around Earth's axis. As Earth rotates, this direction changes continuously in inertial space, because the tangent direction depends on where the point is on the circle. A person standing on Earth's surface is therefore carried in a daily loop in velocity direction, even while also being carried around the Sun and through the galaxy. This daily velocity component is small compared with the solar system's bulk motion through the Milky Way, yet it is significant compared with many familiar speeds. Near the equator, the surface speed is high enough that it rivals the cruising speed of modern aircraft. At mid-latitudes, it remains large. Near the poles, it approaches zero at the exact axis. This gradient is part of why launch sites for rockets are often placed at lower latitudes when possible. A launch near the equator can take advantage of Earth's rotational speed to gain some additional velocity in the eastward direction. This practical detail shows that rotation is not only a conceptual motion, it can be used as a real kinetic resource. Rotation also shapes the distribution of day length. Because Earth's axis is tilted relative to its orbital plane, different latitudes experience different day length through the year. Rotation provides the daily cycle, but tilt determines how long the Sun remains above the horizon during each rotation. This is a link between the daily and yearly layers. Rotation sets the turning, and tilt sets how the turning presents the Sun's path. The result is the seasonal cycle of daylight, a slow change that is experienced through the daily motion. Uncertainty in the basic description of rotation is low. The rotation period and its variations are measured precisely. What remains uncertain in detail is the prediction of tiny changes in rotation rate on short timescales, because they depend on complex fluid motion in the atmosphere and oceans and on internal Earth processes. Yet the overall behavior is known. Earth rotates once per day in a stable rhythm, and that rotation contributes a latitude-dependent surface speed and an axis-defined geometry for the daily cycle. With Earth's daily rotation established as the closest layer of motion, the inward path can now move to slower changes in orientation, the tilt and wobble of the axis that make the direction of the poles shift in space over long times. This next layer shows that even the axis of the daily turning is not absolutely fixed, and it adds another quiet motion to the nested journey. Earth's axis is tilted, and it is not perfectly still. The axis points in a direction in space, defining the poles and the equator, but that direction changes slowly over time. This slow change is not a sudden instability. It is a predictable set of motions driven by gravity and by the distribution of mass within Earth. The most important of these motions is precession, a gradual turning of the axis that traces a slow circle in the sky. There are also smaller variations called nutation and other short-term wobbles. Together, these motions change which stars lie near the pole over long time and shift the timing of seasons relative to Earth's orbit. In the layered journey of Earth's motion, axis wobble is a long clock, slower than the daily turn and faster than the Milky Way orbit. Precession can be understood through a simple physical picture. Earth is not a perfect sphere. It has an equatorial bulge created by rotation. The gravitational pull of the Sun and Moon acts on this bulge. Because the bulge is tilted relative to Earth's orbit, the gravitational pull produces a torque, a twisting influence that tries to pull the axis into a different orientation. Earth's rotation resists this change in a specific way. Instead of tipping straight over, the axis responds by precessing, slowly rotating around a cone. This is similar to the way a spinning top wobbles when gravity pulls on it. The analogy is not exact, but it captures the core idea. Torque acting on a rotating body produces a slow change in the direction of the spin axis. The precession period is long compared with human life. It is measured in tens of thousands of years. Over that time, the direction of the north celestial pole drifts across the sky, meaning that the star near the pole changes. In the present era, a particular star lies close to the north celestial pole and is used as a marker for navigation. In the distant past and distant future, other stars take that role. This shift is a calm reminder that the familiar sky is not permanent. The constellations and the pole star are temporary arrangements from the perspective of long time. Precession also shifts the timing of seasons relative to Earth's orbit. Earth's orbit is an ellipse, and the orientation of that ellipse in space is not fixed. The line connecting the closest and farthest points, the line of apsides, slowly rotates due to gravitational perturbations by other planets. Meanwhile, Earth's axis precesses. The combination of these motions changes the date at which Earth is closest to the Sun and the date at which certain seasonal points occur. Over thousands of years, this changes which hemisphere has summer when Earth is closer to the Sun and which hemisphere has summer when Earth is farther. This affects the distribution of sunlight and contributes to long-term climate patterns when combined with other orbital variations. Nutation is a smaller oscillation superimposed on precession. It arises because the torque applied by the Moon and Sun varies as their relative positions change. The Moon's orbital plane is tilted relative to Earth's orbital plane and precesses itself. This changes the direction of the torque over time, producing a small periodic nodding of the axis. Nutation has a shorter period than precession and smaller amplitude, but it is measurable and important in precision astronomy. It affects the exact orientation of Earth in space, which matters for navigation, satellite tracking, and the pointing of telescopes. In addition to these externally driven motions, Earth's axis experiences tiny shifts due to internal mass redistribution. The atmosphere, oceans, and the movement of water and ice on the surface shift Earth's mass distribution. When mass shifts, Earth's moment of inertia changes, meaning the distribution of mass relative to the rotation axis changes. Conservation of angular momentum implies that changes in moment of inertia can change rotation rate and can also shift the orientation of the axis relative to Earth's crust. This is related to polar motion, where the rotation axis moves slightly relative to Earth's surface. These shifts are small, but they are measurable with modern geodetic techniques. They show that Earth's rotation and orientation respond to fluid motion and to long-term changes such as ice mass redistribution. In the context of what Earth is moving toward, axis wobble adds a new sense of toward that is not spatial but geometric. Earth moves toward a slowly changing orientation in space. The axis points to a slightly different part of the sky each year. The seasons shift slowly in relation to Earth's orbit. Over long time, the pattern of sunlight distribution across latitudes changes. This is not a movement toward an external object. It is a movement of Earth's own orientation, a drift of its axis driven by gravitational torque and by the planet's internal dynamics. Axis motion also changes the coordinates used to map the sky. Astronomical coordinate systems are tied to Earth's equator and poles. As the axis precesses, these coordinate grids slowly rotate relative to the distant stars. This is why star catalogues include reference epochs, fixed dates at which coordinates are defined. Without accounting for precession and nutation, the positions of stars in a coordinate system would drift. The fact that these corrections are built into astronomy is another sign that Earth's orientation is part of the measurable motion of the world. The magnitude of precession and nutation also provides a constraint on Earth's internal structure. The response of Earth to torque depends on how mass is distributed and on how rigid or fluid different layers are. Earth is not perfectly rigid. Its mantle can deform slowly, and its core is fluid. These properties influence how the axis responds and how tides dissipate energy. Therefore, axis motion is connected to Earth's interior, though the connection is indirect in this section. The axis wobble is an observable that reflects both external gravitational forcing and internal mechanical response. Uncertainty exists in the fine details of short-term orientation changes because they are influenced by chaotic elements of atmospheric and oceanic motion. The exact position of the rotation pole relative to the crust can wander due to weather patterns and ocean circulation. Over longer timescales, precession and nutation are predictable because they are driven by gravitational mechanics. Therefore, the main uncertainty is not in the existence of these motions, but in the precise short-term variations around the predictable trends. The axis also ties to the daily rotation described previously. Rotation defines the day. Precession and nutation change the orientation of that rotation axis, slowly altering which part of the sky the axis points to. This adds an additional layer of motion to the daily cycle. The daily motion of the sky occurs around a slowly shifting pole. Over centuries, the shift is small but measurable. Over millennia, it is dramatic in a calm astronomical sense, changing navigation stars and the apparent stability of the heavens. Within the documentary's broader theme, axis motion helps clarify that Earth's journey is not only translation through space, but also continual reorientation. Earth moves through the galaxy and around the Sun, and it also turns and wobbles. Each of these motions changes how Earth is exposed to the Sun, to the sky, and to the incoming particle environment. The tilt and wobble do not change Earth's location in space significantly. They change its orientation, and thus the geometry of illumination and observation. With Earth's axis wobble established, the inward path moves to an even slower exchange that directly changes Earth's rotation rate and the Moon's distance tides. Tidal forces transfer angular momentum between Earth and the Moon, gradually changing the length of the day and the size of the lunar orbit. This next layer is one of the clearest examples of Earth's motion changing over time due to a predictable physical process. In the near term, the phrase moving toward becomes most meaningful when it is tied to tracked conditions rather than imagined destinations. Earth travels through space in layered motion, yet the conditions that change human experience most are not the galaxy-scale drifts. They are the practical environments that can be measured, forecast within limits, and prepared for. In this layer, the future is not a secret point in the sky. It is a set of evolving exposures, the Sun's changing activity, the trajectories of near-Earth objects, and the ongoing physical changes within Earth's own climate system. These are the directions in which careful measurement turns motion into actionable understanding. Space weather is one of the clearest practical exposures. The Sun continuously sends a solar wind outward, and during active periods it can release large eruptions that disturb the space around Earth. When fast streams and coronal mass ejections reach Earth, they interact with the magnetosphere and can induce geomagnetic storms, The physics is well established. Charged particles and magnetic fields couple, energy flows into Earth's magnetic environment, and currents intensify. The consequences are not uniform across the planet. They are strongest at higher latitudes where magnetic field lines guide particles into the atmosphere. The visible result can be aurora. The practical result can be changes in satellite drag, disruptions in radio communication, and stress on power grids through induced currents. Earth moves toward these events only in the sense that time advances through cycles and chance eruptions. The path is not spatial. It is temporal and probabilistic, shaped by the sun's magnetic rhythm. Monitoring makes this exposure concrete. Satellites watch the sun, measuring active regions and the evolution of magnetic fields. Other spacecraft measure the solar wind upstream of Earth, providing warning when a disturbance is approaching. Forecasting remains uncertain because the details of each eruption and its magnetic orientation can only be known well when it is measured directly in the solar wind. Yet the broad conditions are understood. Times of higher solar activity tend to produce more eruptions and more particle storms. Times of lower activity are quieter but not empty of risk. The near-term truth is that Earth moves through cycles of heightened and reduced space weather, and the most reliable preparation comes from resilient systems, robust satellite operations, and careful power grid management rather than from dramatic expectations. Another practical exposure is the set of objects that share the solar system with Earth. Near-Earth asteroids and comets have orbits that can bring them close. Most pass safely. A very small fraction have trajectories that require careful tracking. Modern surveys discover and follow these objects, refining their orbits through repeated observation. Orbit prediction is physics-based and becomes more precise as more measurements accumulate. Yet it is not always immediately perfect because small forces can matter over long time. A small push from uneven heating, where sunlight warms an asteroid and it re-emits heat in a way that slightly changes its motion, can alter its path over decades. For comets, outgassing can act like a small jet. These effects are measurable in some cases and must be included when forecasting long-term trajectories. Earth's motion in this context is simple. Earth moves along its orbit and repeatedly crosses the orbital neighborhoods where other objects may be present. Risk is not created by Earth aiming at an object. It is created by the geometry of orbits and timing. A close approach happens when Earth and an object arrive at the same region of space at the same time. The practical response is steady tracking and updated probability estimates. When probability is low, monitoring continues. When probability is uncertain, more observations reduce uncertainty. When probability becomes meaningful, which is rare, planning can include deflection concepts. The scientific consensus holds that deflection is possible in principle for some objects if discovered early enough, using methods that change an object's velocity by a small amount long before any potential encounter. The key is time and detection. Earth moves towards safety when observation systems improve and when decision processes are clear. The third practical exposure is Earth's own climate system, which evolves as energy flows through the atmosphere, oceans, ice, and land. This is not a cosmic destination, yet it is a direction Earth is moving through because the system changes with physical forcing. Greenhouse gases in the atmosphere alter how heat escapes to space, increasing the retention of energy in the lower atmosphere and oceans. This is a radiative forcing, a change in the balance between incoming sunlight and outgoing infrared radiation. Observations indicate that global average temperature has risen compared with earlier periods of widespread measurement, and that the oceans store most of the added heat. it remains uncertain exactly how regional patterns will unfold year by year because weather variability is large, but the underlying physical mechanism is well established, and the long-term trend is measurable. This climate exposure is different from space weather and asteroid risk in tempo and form. Space weather is episodic. Asteroid risk is rare but potentially severe in specific cases. Climate change is gradual yet persistent, altering baseline conditions for heat, precipitation patterns, sea level, and extremes. Earth moves toward different averages and different distributions of extremes as the system responds. The near-term practical meaning lies in adaptation and mitigation. Adaptation includes infrastructure designed for heat and flood conditions, water management, and health systems that respond to changing risks. Mitigation includes reducing emissions and increasing carbon storage where possible. These responses do not change Earth's trajectory through the galaxy, but they change how Earth's people and ecosystems experience the physical environment. There are also near-term exposures that connect space and Earth more subtly. Solar ultraviolet and X-ray variability affects the upper atmosphere, changing density and thus satellite drag. Geomagnetic storms can accelerate this effect. Space debris in low Earth orbit becomes more hazardous when orbits shift unpredictably due to changes in drag. This is a human-created environment embedded within natural space weather. Earth moves toward a more crowded orbital region as more satellites are launched. The practical truth is that collision avoidance and debris mitigation become increasingly important. The physics of motion remains the same, but the environment becomes more complex. In this layer, the word stranger can remain calm. The strange part is that Earth's most meaningful near-term futures are shaped by signals and forces that cannot be felt directly. A solar eruption leaves the sun and crosses space, and Earth's magnetic environment responds hours to days later. A small asteroid a few hundred meters across can be detected as a moving point of light, and precise tracking can turn that point into a predicted orbit decades ahead. A change in atmospheric composition measured in parts per million can shift the energy balance of a planet and reshape climate statistics over decades. These are not stories of mystery. They are stories of measurement turning invisibility into knowledge. Uncertainty is part of each exposure and must be held without exaggeration. Space weather prediction remains limited in the details of event strength and magnetic orientation until measurements are made closer to Earth. Near-Earth object risk is dominated by incomplete discovery for small objects, and by the long-term influence of subtle forces. Yet the largest hazardous objects are increasingly well catalogued. Climate projections include uncertainties in regional outcomes and in feedback strengths, but the direction of forcing from increased greenhouse gases is clear. These uncertainties do not justify alarm in the narrative. They justify continual observation, improved models, and practical planning. Earth's layered motion sets the background. The planet moves through space at high speed in human terms, yet the near-term exposures that matter most arise from local dynamics and local choices. The sun's activity waxes and wanes. The solar system contains many small bodies with predictable orbits that become safer as they are tracked. Earth's climate responds to changes in energy balance. In these realities, moving toward becomes a phrase of time and preparation. It points toward better measurement, better resilience, and a clearer understanding of what can change and what remains stable. The inward path now prepares to close. After the practical future layer, the final synthesis returns to the core meaning of direction across all scales, gathering expansion, cosmic drift, galactic orbit, heliosphere, and Earth's own cycles into one steady, non-sensational perspective. Earth moves through the universe in nested layers, and the meaning of toward changes with the layer. At the widest scale, the universe expands, space stretches, and the average distance between unbound galaxies increases with time. Expansion does not point toward a place, it changes a scale. In that expanding frame, Earth is not headed toward a cosmic center. Earth is part of a bound island of matter, and the rest of the universe recedes on average as the scale grows. The first truth is that the largest motion is not a journey to a destination. It is a changing geometry that can be measured through redshift and distance. Against that expanding background, gravity creates motion that does have direction. Matter flows toward denser regions of the cosmic web and away in a relative sense from voids that pull less. The local group of galaxies is a bound system within this web. It has its own bulk motion relative to the cosmic microwave background, and that motion is imprinted as a dipole pattern in the oldest light in the universe. The cosmic microwave background provides a practical rest frame, a calm way to say that the solar system is drifting through space with a measurable heading and speed. That heading is not a place to reach. It is direction defined by a temperature gradient, a kinematic signature of motion through ancient radiation. Within the local group, Earth's motion is carried by the Milky Way, a galaxy shaped largely by dark matter. The Milky Way and its neighbours are bound, and within this bound system, gravity draws the dominant galaxies into closer interaction over long time. This is one legitimate meaning of toward Earth moves with the Milky Way in a group that evolves toward a future where its largest members interact more strongly. This is not a sudden event. It is a slow gravitational convergence measured in billions of years, a quiet rearrangement of mass inside a bound island of space. Within the Milky Way itself, Earth's motion is carried by the Sun's orbit around the galactic center. The Sun follows a long path through a structured disk with spiral patterns that evolve over hundreds of millions of years. The solar system travels through different regions of the galaxy, sometimes nearer to dense star-forming lanes, sometimes in quieter inter-arm space, and it oscillates gently above and below the disk's mid-plane. This layer provides a concrete sense of movement through a real environment. Earth is moving toward new stellar neighborhoods and new interstellar conditions along a path defined by gravity. Within the local stellar field, the Sun also drifts relative to nearby stars. That drift gives the solar system a local heading. Along that heading lies the interstellar medium, a thin but structured mixture of gas and dust. The solar system moves through patches of different density and ionization, and those differences reshape the heliosphere, the bubble carved by the solar wind. The heliosphere is a moving shield that modulates energetic particles and helps define the space environment of the planets. At this layer, toward means moving toward different boundary conditions, toward regions where the external pressure on the solar wind differs, and where the shape and size of the heliosphere adjust. The change is subtle on human timescales, yet it is part of the real environment through which Earth travels. Inside the heliosphere, the most noticeable variations come from the Sun's magnetic activity. The solar cycle changes sunspots, flares, coronal mass ejections, and the texture of the solar wind. These changes modulate cosmic rays and shape space weather. Here, toward means moving forward in time through cycles and occasional storms, it is not a journey toward a distant object. It is a passage through a changing magnetic climate that can be measured and, within limits, forecast. Closer still, Earth's own motions dominate daily experience. Earth orbits the Sun each year, a stable loop that changes direction continuously and forms the baseline for seasons. Earth rotates each day, carrying every location across a latitude-dependent path and producing the rhythm of light and darkness. Earth's axis slowly precesses and wobbles, shifting the sky's geometry over long time. Tides and internal mass redistribution alter rotation subtly. These are not cosmic drifts. They are the local mechanics of a living planet in motion. Toward at this layer is the next sunrise, the next season, the next slow shift of the axis, the next quiet adjustment in timekeeping as rotation varies. The practical future adds a final meaning. Earth moves toward conditions that can be tracked: solar storms, near-Earth objects, and ongoing changes in climate forcing. These are not destinations. They are evolving exposures. They become less mysterious when measurement is steady and when uncertainty is held within evidence. The strangeness in the title, in this calm view, is not that Earth is headed for an unknown cosmic wall. The strangeness is that motion is layered, and that the universe offers many frames in which the same motion can be described. It is strange that ancient microwave light can define a rest frame. It is strange that a thin interstellar medium can shape a vast heliospheric boundary. It is strange that a planet's rotation and axis wobble are both stable enough for navigation and flexible enough to require correction. These are measured strangenesses, quiet and precise. The true meaning of what Earth is moving toward is therefore not a single answer. Earth moves toward the next point on its orbit and toward the next turn of its rotation. Earth moves toward the next phase of the Sun's cycle. Earth moves through interstellar conditions that slowly shift the solar wind boundary. Earth moves along the Milky Way's orbit and through the galaxy's changing structure. Earth moves with a bound group of galaxies that drifts through the cosmic web. Earth participates in an expanding universe where distant unbound galaxies recede as space grows. Each layer is real, each layer is measurable, and each layer changes the meaning of direction. In a calm synthesis, the journey is not a chase and not a prophecy. It is a steady motion through nested environments. The universe is not waiting ahead like a single strange destination. The strangeness is already present in the way motion can be read from light, in the way gravity organizes flow, and in the way a small planet's daily turning is part of a trajectory measured against the oldest radiation in the sky. Earth moves, and the motion is both ordinary and immense. The night sky remains quiet while the planet turns. The orbit continues while the solar wind flows. The heliosphere holds its shape and shifts gently. The galaxy rotates, and the local group drifts. Expansion carries distant light farther away. The layers remain, each one steady in its own time, each one calm in its own scale. Rest comes more easily when motion is understood as a rhythm rather than a threat. The universe does not rush. It changes with patience. Earth travels within that patience quietly, continuously, through space and time.